So recording has started. So welcome again. So today we are we will talk about writing the program further. Yeah. Uh, but before we'll get into the coding, into the slides, and maybe revert back of what has been done. Yeah. We haven't seen for 2 weeks. Yeah. Do you have any questions about anything? What do you mean by project work? Yeah, it was mentioned something. Yeah. I think that it will take the form of this last assignment. Yeah, because it's a little more involving because it deals with working directly with this code. Yeah. So typically, I go a little further with this program, yeah. But this year, I think that we have analyzed more numerical methods than usually we do, yeah. And also, we skipped one classes last week, yeah. And we have only one classes to go because in 2 weeks I'm again traveling, yeah. So we won't have classes in 2 weeks. Yeah. So I think that let's see how far we will go today, but I don't think that we'll go uh, extremely far, like doing all the dynamics. Yeah. So I think that will just the project will mostly involve kinematics. Yeah. Maybe for after next week there will be very small addition for dynamics. Let's see how far it will go. And because we don't have the last classes and you might have some questions or tasks, yeah. So I think that we should discuss next week about maybe organizing some kind of, just hands-on session or question and answer session, yeah. If you are struggling with the things that were up to now or whatever can be the issues, yeah. Okay, makes sense?
Project is basically then solving this, and then also probably reports. Report then similar to the exercise reports.
Yeah.
Okay.
Yeah. It does work for you?
Yes.
Of course, if you want to do this in group work, we can go for it, but I'm not sure if this is, needed or if you prefer to go that way. Okay.
When will be the deadline for the
We can discuss this as well. Yeah, because is there any deadline for you to get the grades? I don't know. Okay, yeah, of course. Then you can let me know. Yeah. Uh, uh, Because as far as I recall, yeah, like in the last year or last 2 years, yeah, I put the grade in CISO at the end of January, and I get almost no complaints. Maybe exactly like that. 1 or 2 person ask if they wanted to have it earlier because of like 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 whatever. Yeah, I don't remember. Yeah, but in general, I just closed the case at the end of January. So of course you don't, if you, it would be the sooner the better. Yeah. So there will be the deadline, but as you can, resubmit those assignment until you are satisfied. Yeah. Then I'll keep it until end of January. Okay. Okay. Perfect. Uh, okay. I can see any comments or questions from the online participants. So let me share the screen. And let's try to recall what we have done last time. Yeah. So then this is very similar presentation to what was shown last time as well. And the reason is that we are still working on the same. So we are working on planar kinematics. Again, kinematic analysis, solver implementation. I hope that all this is, known, yeah, that we work in Cartesian coordinates, yeah, and for the code, we already make this by having, body positions, yeah, and when we have initial positions, then we are extracting all those coordinates as Cartesian coordinates on the planar, yeah, that describe the position of certain point of the body and rotation with respect to global coordinate frame. Then we have this transformation matrix, yeah, like we should have it already, yeah, like rotation matrix, yeah, that exactly code this cosine minus sine, sine, cosine, yeah, this formula. And then we can use this formula to transform back and forth vectors or points, or in practice we transform vectors, yeah, that indicate some points back and forth between local coordinate frame and global coordinate frame, yeah. And for transforming from local to global, we use this matrix as it's written here, yeah. And for using it in opposite direction, so from local to global, yeah, from local to global, we use inverse of this transform. And because of the properties of this matrix, it's just transpose. Yeah. Here. Then for kinematic analysis, we need joints. Yeah. And again, where's our laser pointer? It's here. Yeah. And one of the very basic joint types is revolve joint, as shown here. Yeah. It says that, looking from both bodies, yeah, from the side of both bodies, we want to have one point in common, yeah, and one point in common, it means that those the bodies can just rotate with respect to this point, yeah. Next one, not to overcomplicate, we have those simple constraints that we are yet to implement, as far as I remember. Uh, yeah, and simple constraint, as name suggests, takes this simple form, yeah. Uh, Driving bodies, we also need driving bodies for kinematic analysis, yeah, because by design, yeah, if you have any kind of mechanism, yeah, by definition, mechanism should move, yeah, so it cannot we cannot constrain all the degrees of freedom. And if we won't constrain all the degrees of freedom, then of course, if we want to solve for position, it's not well-defined problem, yeah, because we don't have full rank Jacobian matrices. So to fully define the problem, we have to add those kind of driving constraints saying that something is moving in certain way. Yeah. Uh, then we can perform for kinematic level position, velocity, and acceleration analysis. Yeah, that makes the most sense. The most challenging is position analysis because it includes a solution for a nonlinear set of equations. Yeah, and we will use Newton-Raphson for it as our target. Then having solution on the position, yeah, we can get solution on the velocity level, yeah, using this relatively simple formula, or acceleration analysis using this a little more involving formula, but it looks, I think, far worse than it is in practice. Position derivatives, we need them for various purposes. But I think that we can out of this we can just get to our example analysis, and if we will have to go back to those position derivatives, then we'll get there. Yeah, but I think that we also describe about this, so this is just for a quick recap of what is going on. Yeah, so this is our example analysis, and once again, yeah, why we use this as example. Yeah, we are coding in the way that our driver file that now we are putting all the information about those mechanisms. So we are putting information about the bodies, then about the joints, and then we'll also put the information about properties of the analysis that we want to make. So for example, time step of our kinematic analysis, time range, and so. By exchanging this driver file to another file, yeah, we are able to solve different kinds of mechanisms. Yeah. Okay. So I hope this is clear. And now let's get back to code. Any questions? Everything's clear? Yeah, so of course for this coding we made some design choices. Yeah, maybe not all of them are optimal, or not if we have some discussions. So not all of all of those decisions suits everyone. But well, it is what it is. Yeah, when you're writing program, there is plenty of decisions to choose. Yeah, to make. Yeah. But in short, we make coding in the way that here's our driver file, yeah, that includes information about our system, yeah. Not all parts are yet available, yeah. But it has the form that firstly we make the system, yeah. So here we have the firstly it create the system, and yeah, as it's written here, it creates empty system. So it's placeholder that where we put all the information about what we need for analysis. Yeah. So the next stage is to add bodies. Yeah, and we decide that we'll identify our bodies by their names. And then after the name, it follows the initial position of our body, provided as position of this its characteristic points and rotation of the frame that is put in this point. Okay. And for our slider crank, we may use four bodies. Yeah, we also make this kind of decision that we will also add to the system special ground body. Yeah, then we'll constrain it. Typically, it's hidden implementation detail. Yeah, because we don't need this body. Yeah, we could write without this body because it's very specific body. Yeah, because it's immovable. But adding this body allow us to write constraint in simple form. Yeah, because if we wouldn't have this body, yeah, then we have to write that if body I, because let's say that we have revolute joint, yeah. So if we haven't, now we can just write that revolute joints connect two bodies, yeah, and then we have one equation, yeah. But if we wouldn't have, ground body, then we need, to write that if first body is the ground, do this. If second body is the ground, do that. And if no body is the ground, do the last stuff. Yeah. So adding ground, yeah, while we have to for this simple case, we have to remember about this, about adding this and then constrain it. Yeah, it simplifies the coding process, especially for the constraint. And constraint are the most involving here. So we add the ground body and then three body of the mechanism, three moving body of the mechanism. And after adding those bodies, yeah, we have them here as expected. Then we can get initial positions, yeah, which of course stack all the information that we have provided here in the order in which we have added those bodies. Then we have joints. Yeah. So we have written the equation for revolute joint, yeah, and based on our slides, we identify that for writing this equation, we need information about, of course, which bodies are connected. Yeah, we always need this information, where the constraints are pointed. And we identify that this information is characteristic of the body, the same here. So we just need the information about those two vectors. Yeah. So what are coordinates of those vectors that identify this joint? Yeah. So we provide those two information here, local UI, local UJ, yeah, and we made it based on our plot. And then it is adding silently to our system constraints. Yeah, and we have three revolute joints. Yeah. And then when adding revolve joints, instead of keeping the information about the body, we decided we don't need it for the equations. We just need the information about the coordinates, of course. Yeah. So we just keep here the information about body indices to get those coordinates. Okay, and with all this information, we can write constraint equations. Yeah. So for our level joints, so we add 3 level joints, so we are expecting to have 6 coordinate equations, constraint equations, because those are vector equations. Yeah. So within this one vector equation, we have 2 algebraic equations. Yeah. And we can see it here. Yeah. And of course, because we use quite cruel approximation about those coordinates. Yeah. So we haven't specified them so carefully, like we didn't follow, the exact geometry. So those constraints are met, aren't met at the initial stage. Yeah, but then we'll solve for them. And the next step is to add simple constraints. Yeah, so we already have added here the functions. Yeah, so but I don't think that we have coded it. Yeah, exactly. We haven't coded it. So and we decide that we'll add those constraints in the way that we add, of course, that system, then we provide body name, that then we provide what coordinate we are going to constrain, and the value of this coordinate. Yeah, it follows exactly those equations. Yeah, that those simple equations are always keeping an eye that specific coordinate has just provided value. Okay, any questions up to now? So let us implement this function. And as we described, yeah, this characteristic variable, this structure variable says, has to be passed back and forth because of how the coordinates are handled within the MATLAB, because they are handled on as this kind of by copy. Yeah. Uh, so yeah, if we make any kind of modifications to the sys variable, and we'll make them by adding those constraints, we have to give them return them back so that those changes are recorded by the parent scope. Okay. Let's save it. So yeah. So now what do we need to store? What information do we need to write this kind of equation? I think that you are overcomplicating the things a little, yeah? Because take a look, here are the simple constraint. The name came from the fact, as it's shown here, that they constrain directly coordinates. Yeah, so they are not very general. Yeah, so they are useful in the cases that are relatively simple, like in some of our cases. Yeah, so yeah, they constrain directly coordinates. Yeah, So you don't have to go from the coordinates anywhere else, like in the case of, for example, those revolved joints. Yeah. So here you just have two information if you analyze it. So first of all, it's coordinate itself, and coordinates are in Q vector. Yeah, so the first information that we need is coordinate index, because then we can get it from the Q. Yeah. And the second information that it's needed is what should be the value of this coordinate. Is it correct? Yeah, so those are only two information that we need. So our simple, we need coordinate index. Yeah. And then we need so we need coordinate index and coordinate value. How do we get coordinate index? Yeah, so we, as I remember, we had some function, I think we used it here, yeah. But the index, yeah. So, okay, so we could redesign it to get body index directly from the name. I don't know if you want to do this. Hmm? We have already quite a lot of functions. Yeah, maybe adding one more wouldn't, wouldn't be so bad. So maybe because we will use it here, we'll use it on the simple constraints, and then we'll use it in many other places. Yeah. So let's write a function. Yeah. That return, how should we call it? Yeah. It will be almost like that. So it will be body. For example. Yeah. So we will provide our body index from name, and it has two stages that are explained here. Okay. Yeah. And then we can immediately use this function here. Okay. And then we can use it here. Perfect. Okay. Makes sense? But now, what is body index? Hmm?
But not maybe like depending on the coordinate next second or third.
So body index is, so it's a vector. that contains 3 values. Yeah, it contains 3 indices. Yeah, but we need only 1 index for each simple constraint. Yeah, so how to get this index? Yeah, from coordinate ID. So we can just write maybe just simple if statement. Yeah. So firstly, we need to initialize some value, or maybe we even don't have to. But then we can write if is equal to x, then else if is equal to y, then and else if is equal to phi, else error. Hmm. Yeah, you're right. Of course. Yeah, it's coordinate ID. Yeah. Does it make sense what this code is doing? Perfect. What are the issues with this code? When this code fails? I don't know if we, it's a good question if we have, maybe it doesn't fail. Let's see. Yeah, it fails here. Or not. No, we have it. Yeah, so we already have it. So it shouldn't fail, because I was thinking if it fails when body name is incorrect, but it seems that it will return error, and so we will get the information. If coordinate ID is incorrect, we have error here. Yeah, coordinate value, well, yeah, it doesn't check if it's not a number or infinite, but maybe we don't have to go to such extent. I don't like one thing about the code that we are writing here a little, yeah. That, for example, that here when we are adding bodies, it doesn't check if the body exists already. Yeah, I think that it would be nice to add it, but maybe let's leave it for later, yeah. Uh, but I believe that now, it should work, and if we run this, it should add 5 of those simple constraints. Yeah. So let's see. So we get no error, and this is what we expect in practice. And now we are expecting that in our system structure, there are here 5 simple constraints, but they aren't there. Why?
Into the system.
Exactly, we haven't added them. So yeah. So let's get back here, yeah, and the same as we were adding revolute joints, yeah, we have to also add our simple joints, simple constraints, yeah. So we have sys constraint simple, yeah, simple, and we have to add here our simple. Again, when we get back here, yeah, and run this part of the code and analyze our system, yeah, we have 5 simple constraints, yeah. And we can open this, and we can see that we have simple constraints that constrain our indices 1, 2, and 3 to 0, which means that our first body ground will be always there, and so will be always put at the origin of the global coordinate frame and with no rotation. So then, we can safely relate to it. And those last two means that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yeah, that those two coordinates. So the coordinates of the slider are also kept on those values 0. And it of course means that for our example of slider crank, yeah, our slider coordinate 11 is related to its y displacement, yeah. So it means that it cannot move along this axis, yeah, and so it will always be on this line equal to 0, which we wanted to have, and then it cannot rotate. Perfect. Now, of course, we would like to have, we're adding those joints to have constraint equations, yeah. But of course, and we have them. Okay, so it seems that we already add those constraint equations. I wasn't expecting this. Okay, yeah. So this code is not working properly, at least. It shows proper results by means that those are zeros, yeah, but really it doesn't work. Yeah, so this is again, that we get good results, but with no good reason, yeah. Because we got good results because we are expecting to get 0. But yeah, it works only from this point, yeah. So it means that we are calculating the number of the constraints properly, exactly as written here, yeah. But we don't really have proper handling of those simple constraints here, yeah. So we have to write those equations here in addition, yeah. So we will add another loop as for s equal to sys constraint simple, yeah. From this, we know that we can get two information from from the structure. Yeah, so we get we have to decode the stuff, and now it's not helping so much. And then coordinate value, we have to reverse it, is equal to s coordinate value. Make sense? Yeah. And then those constraints are so simple that we can immediately write them. So what should be written here? What should I write down? Maybe I cannot hear it very well. Yeah, but what should I write here as a concept? Yeah, yeah, equation for the constraint. Yeah, and where we gather our constraint equations. Yeah, yeah. This is how it looks like. Yeah. So Q, I think it's yeah, it's small q, a lowercase q of coordinate index minus coordinate value. Yeah. And where to put this equation? Yeah. Okay, we are storing this into C vector. Yeah, we are just storing this into C vector because this is our returning. Yeah. And of course, it's written on all those slides. Yeah. Like here. Yeah. So we are storing this into our C. And now you are referring to where to put it. So we put it at current index plus 1. And then at the end, we are increasing the number of coordinates. Yeah. And to avoid for the future the case that the code runs despite it's not computing all the values, yeah, we here can write assert, because we know that the number of the constraints should be equal to current index minus 1. No, it should be equal to current index. No, I think it should be equal to current index. We will check it very soon, yeah. So we'll assert that short explanation, and then we'll provide, I think it should be vector. Okay. Is it clear why I added this last assert and what does it do? What do we do?
Just make sure that you have the signed off constraint equation.
Yeah.
Basically, each join has been assigned a point amount of.
Yeah. Yeah, because previously we have this kind of part of the code, yeah, without this, and still the code works, yeah. So now when you try to run it, okay, so it seems that this assert is not written properly. So how should it be written? One of those things that will it work now? Yeah, now it works. Not all constraints were assigned. Our constraints 11 assigned constraint 6. And now, if we return back with this, no, it's not that one. Maybe okay. if we return with our simple constraints, yeah, hopefully yeah, we get no more complaints, and still the vector looks the same. Yeah, but at least now we are kind of sure, at least more certain than we have done what should be done. Okay, so let's move forward. Yeah, the last thing that we are missing is adding driving constraints. Yeah, so driving constraints. The main difference for our case is that instead of having coordinate as the case of the simple constraint, we have function of time. Yeah. So adding this, I think, will be extremely straightforward. Yeah. So we would like to add them. So here is our header, body name, coordinate ID, and coordinate function. So it's very similar to the simple constraint. Yeah. We need two fields. We need coordinate index. Yeah. So driving symbol. Yeah. We need coordinate ID and coordinate function. Yeah. And of course, coordinate function is coordinate function. But we need index. Yeah, but index works the same way, that based on the name and coordinate ID, we need coordinate index. And of course, we have this code here. So what should we do? Exactly. Yeah, we should make function out of this. Yeah. Save as for example, body coordinate from name that provide us index based on this. So it makes it nicely. Yeah. So this refactoring works pretty well. Yeah. So with this refactor function, we can get back to here. But as proper refactoring works, yeah, it's already replaced with what we have. And now we can just copy paste this function. And it's done. Yeah. Okay. So, and now there is the last step that we almost forgot in the last part, yeah, is to add this constraint to the set of constraints. Yeah. Driving is equal to sys constraint driving simple. Yeah. And now we are done. Yeah. So now we are done. So this code should work. Yeah. And now when we take a look on our system, we have one driving constraint that drives our constraint ID of index 6. Yeah. And it means that based on our description of the system, this is the angle of the crank. Yeah, because simply 1, 2, 3, 4, 5, 6. Yeah. So it drives the angle of the crank. And now Again, we should be able to calculate constraints. Simple and driving constraints, yeah. And as expected, we get the error because we add one constraint, so we're expecting to have one more constraint, yeah. But we haven't implemented there, so we have to get back to our constraints function, yeah, and add new loop for driving constraints, yeah. So this loop will be very similar to simple constraints, but of course it's for driving. So for driving, coordinate index is exactly the same, yeah. So like, no issues here. But for the second value, we have coordinate function. And next, yeah, this is part the same. Then we need coordinate function. And because it's a function, it has to be called. So what is argument of this function? Yeah, it's t. Exactly. So now, after adding all those coordinates, we run this again, just to make it apparent. Yeah, so we can run it again and get no error. And we get the proper value of our last coordinate. Yeah. So we have our, yeah, it's added. Yeah. So it works. Perfect. So now that we decided that, we will also write the function that it's called check system. Yeah. But we don't have this kind of the function. At least in the check system for the kinematic analysis, we check if the number of coordinates is equal to the number of constraints. So that's why we're sure that we can, progress with the solution. Yeah. So we need new function check system. Yeah. And to check this simply, we need number of constraints equal to, okay, this is function is n constraints of sys and coord equal to n coordinates also for our system. Yeah. And then we can put here simply assert n coord equal to n constraint. Yeah. And then make error message. And then Again, put those values for display. So it also means that now when we run it, it works well. Yeah. But then if you were to remove this and then run all this file again, okay. Yeah. We get this kind of nice error that the number of coordinates 12 does not equal to the number of constraints 11. Yeah. And when we remove it, we get totally different error, and it's connected with the fact that here we are trying to do something that we haven't prepared for. Okay. But this part we have checked. Yeah. So now we hope that this will work. Yeah. So simply, as you may recall, we want to solve this in time, and we want to solve this using Newton-Raphson, but it's totally solvable using fsolve. Yeah. Good thing about this is that we can now we have a nonlinear equation, we have coordinates, we can solve it. Yeah. And we don't need particular Jacobian matrix. Well, we need it for further, further analysis. So still we will calculate this Jacobian matrix, but at this stage we should be able to run this code. But let's see if it runs. Yeah. Okay. So it wrote equation solved, fsolve completed because the vector of function values is near zero. Nice. As measured by the value of the function tolerance, and the problem appears regular as measured by the gradient. Nice. Yeah. So in short, it's written that problem is solved, problem looks to be irregular, no issues. Yeah, so nice. Yeah. So now we have some Q, and we can compare it with Q0. Yeah, of course. Yeah, this is one thing. So of course there are some differences. Some of them bigger, some of them smaller. Yeah, but they look somehow reasonable. What is the very basic check for the Q? If the Q is reasonable. Hmm? Equal to what? Yeah, what we are solving for. Yeah, exactly. So we are not expecting that constraints are fulfilled. Yeah. So so again, let's copy that part. Because again, we want to solve constraints for our system. Now we don't want to solve it for Q0 because we know it. Q0 was just our rough approximate. Yeah, so we want to solve it for Q that came from QSolve. Still, it's at time equal to 0. Yeah. So okay. So is it something that we are expecting to get? Yes, of course. It's numerical 0 with quite good tolerance. Yeah. We cannot expect it to be 0 perfectly. Yeah, we have seen it many times. We are dealing with numerical methods, so this is only that we can hope is for numerical zero. That's good. Yeah, and of course, if we put here 0.1, then we get some value that is large enough that it's not zero. Yeah, but is yeah, yeah. But of course, with this Darby constraint, all the Q has to be changed to account for it. So now we should, solve for kinematics. I think that the next thing that we can do is to solve for kinematics forward in time using F-solve. And then we can replace it with Newton-Raphson, but to replace it with Newton-Raphson, we need Jacobian. Yeah. Okay. Makes sense? So it means that you want to write a function, yeah, that provide us time vector, t, that provides us with the coordinates matrix, yeah, for subsequent times, yeah. And what is this function? How to call it? Uh, solve kinematics. I added here also this f-solve because it's not our target, yeah, because our target will be to solve kinematics using Newton-Raphson, yeah. So that's why I add this f-solve. So then not to replace it, yeah. Then we can delete it if needed, but let's keep it that way, yeah. So of course it requires a system, yeah. And what else does it require? No, no. Because of course. Okay, so depending what do you mean for it. We solve this based on the constraints. This is clear, yeah. But system is enough to get constraints. Almost enough. Yeah, but it also requires Q0. Yeah, yeah. So it requires Q0 because no, it doesn't require what I'm talking. Yeah, because we will get Q0 also from the system. Yeah, so that's true. It required, for example, this span. Yeah. So yeah, then that's all I think because then we can get Q0 based on our system. We have done it. We can get constraints based on our system, and then we have to get the information about the time. Yeah, or we can get T end and so end time. Yeah, end time step. Yeah. Now, of course, we have two options. Yeah, we can either pass those information like that, or we can embed this information into our sys. Let's leave it that way. Okay, let's leave it that way.
Test with different time steps, whether we just have it outside of this.
Yeah, so okay, there are no comments from the audience. So for how long do we want to solve our system? Okay, let's see what is maybe omega. Omega was 1.2 radians per second. So to get the full rotation, we need like 5 seconds. Yeah. Okay, we can solve it for 5 seconds. And time step? Okay, 0.1, yeah. Of course, it cannot be too large, because if we get too large, no, it will jump so much that we might not be able to solve it, but then we'll run into some issues or get some very irregular plots, yeah, so we can check it. Yeah, and of course, if it's too small, then we get abundance of points that are not needed. But okay, let's see. We can start with 0.1 and then check if it makes sense. And of course, we have to implement all this stuff. So let's close all others. Add here function. And now we can start implementing the stuff. Yeah. So what should I write first?
Zero.
Okay. Initial position based on system. Okay, we have Q0. What? Yeah, we have to define T. So C can be defined, head start. Yeah. So in practice, to define T, we need to know how many we need time samples. Yeah. So we need the number of time steps. Yeah. Or we use also NT. And as far as I remember, we use this kind of formula, and time divided by time step, maybe +1, yeah. And then we can define that T is linspace of 0, yeah, something like that. Will it work? We'll see if it will work. It should work. Looks reasonable. Yeah. Now we can define what is Q. Yeah, what is Q? What is the size of Q? Because we want to pre-allocate it. What is the first size?
Zero times T.
Okay, length of Q0 and T. And now what should we do?
Start a loop.
Yeah, I think so. If something will be missing in the loop, then we'll get back to it, but it looks like we have everything or almost everything, yeah? We are not assigning Q0 to Q, because we assume that for kinematic analysis, this doesn't have to be consistent with the constraints, yeah? So for II or IT equal to 1 to NT, yeah? So we know that T is equal to T of IT. We need it for constraints, yeah? And we also need that stuff. We have already done it, so why not? Yeah. Maybe it could work, but what is issue with this code? Can you spot the error? Yeah.
Q.
Yeah. Yeah, you're perfectly right. Yeah. So here we should sign that Q is equal to Q0. Yeah, and then we should use Q internally. It might even work, this code, but it's far from being a good solution. Yeah, that we would like to always start with the initial position. Yeah, because as it moves, it can move quite a lot. Yeah, this is quite simple. This system is pretty simple, so it might even work without it. Yeah, but in general, it's very bad idea, and for sure, it's not good for efficiency. Yeah, because finding incremental solution, yeah, will be always much easier than finding the solution that is far from our required one. Yeah, so it's always a good idea. Yeah. So yeah, so for sure we need some running variable q. Yeah, we can use qc and q if needed. Yeah, but at this stage I think that we don't need it. We can just, especially for fsolve, work that way. Or to make it more apparent, we have q. But okay, is it clear, or should I introduce some current running value? Yeah. So now what we are missing still? Yeah. Yeah. We have to provide solution from the outside, yeah. So we have to put this value in this matrix. So Q of all values for point IT is equal to Q. And it should work, yeah. So let's run it. Okay. Good point is that we don't get any errors. We get a lot of those calls that the question is solved. Uh, it's good, yeah. So it means that the equation is solved. We have T.
The activity of Q0 should be inside the for loop.
You mean about this part?
Yeah, the line 11 should not be inside the portion.
No, for sure not. Yeah. Yeah. So this would be detrimental to efficiency, yeah, and can cause convergence issues.
Solving the system doesn't start by, let's say, the initial position. We want to be
So, okay, so the reason is that let's say that we analyze train, okay? Yeah. So train starts here, yeah? But let's say that after 2 hours is 200 kilometers away, yeah? I think it's reasonable, yeah? So if you want to analyze this kind of the system, yeah, it's not good to start at the beginning, yeah, yeah. So and then if we had this Q0 inside, it would mean that we were always trying to figure out where is the train after 2 hours, based on the knowledge when it was at the very start, yeah, and this may fail because it's just so long time and distance that it's hard to relate to those variables anymore, yeah. And by leaving this q0 outside and referring to q, and q is always our current or last solution, yeah, then it means that we are analyzing, the train that it's, like, 59 minutes away to 1 hour. Yeah. So this means that now we are working with those, the values that are much closer to the next ones. Yeah. Yeah. So maybe I will write it still. Yeah. So it means that we have Q current. So for last. Yeah. So here we have Q last. Yeah. And then we have to here Q current, and then we have to simply write the Q last is equal to Q current. Okay, does it make clear? Yeah. So let's leave it that way. Of course, for efficiency reasons, but we don't care so much. Yeah, either case, multibody problems are small. It's not like we have CFD with billion of degrees of freedom that we need supercomputer. Yeah, and readability is the most important here. Okay. So now it shouldn't change at all results. Let's check. Okay, it's still working. Okay. So let's first examine our time vector. Yeah, but I think it looks reasonable. Yeah. So it makes those increments as we required 0.1. Yeah, very, very nicely. And it gets up to value of 5. Perfect. Yeah. And of course, this +1 is to account for the starting point, and that both points are inclusive. Now let's take a look at Q. Okay, so Q has some values, but well, we cannot say a lot about it. Yeah. Yeah. Can we say a lot about this? I think not really. Yeah. So let's make some plots. Yeah. So let's make some basic post processing. Yeah. Well, I think that one of the best things we could do is to calculate the norm of the constraints if they are met. Yeah. Because we of course are expecting that plot of t q of 1 so we are expecting this to be 0, yeah, because this is first constraint is ground, yeah. And as you can see here, it's numerically 0, yeah, because I'm sure that it's not very good for the, especially can't see it, but it's clearly 10 to minus 80, yeah. So it's like really numerical 0. Then of course Q2 10 to minus 19, I believe, yeah. And then we can go like this for longer. But I think that the better would be to check constraints, yeah. So we'll check if value of the constraints at each time point is sufficiently near to 0, yeah. But then we would get the matrix. It's again not good, yeah. So we'll check if the norm of the constraint is equal to 0 at each time step, yeah. So calculate norm C. I make some shortcuts. Yeah, so norm C it will be zeros of size of t. Yeah, and then we'll run a loop. Again, we get the value of t, and then we calculate constraints for the system. Q are all the values of time it. Yeah, did I get this index right? Yeah.
The things to be solved kinematics and so.
Could you repeat?
Would it just be better to also pass the C, the constraints to the solved kinematics at so that they solve the constraints during the.
But it solves constraints.
Yeah.
And And do you mean that we should output this here or something like that?
We could,
Yeah. But it's not very profitable because it should be zero. Yeah. So in general, we are not very interested into it. So here we are just post-processing this to, yeah, to check if it works. And to get this nice figure that, I don't know how to change those. Okay. It would be nice to maybe to change those values because even at my resolution, they are not so easy to follow. Yeah. But I can tell you that this is 10 to the minus, I believe, 8. Yeah. So, okay. So at least it seems that the constraints are met nicely. Yeah. Well, to expect anything else, but that's good. Yeah. It will be especially nice to check it when we will implement it using Newton-Raphson to check at least partly if our Jacobian is correct. Yeah. But that's good. So, okay. Now, how to check how our system is moving or if it's moving properly. Or the way that we intended. Yeah. Because we have some intuition about how our system should move. Yeah. So here is our system. Yeah. And we are adding omega here. So we're expecting that this body to move this direction, yeah, this body to follow it, and the slider to move here and back and forth.
angle is actually turning like we want it.
Yeah, yeah, that's true. So we can check the angle. Yeah. So what is index of our angle? Yeah, I think it's 6. Yeah. We can even use our helping function. I think it's that one. Yeah, we can even use it to get it without re. So for the system, body name is crank and coordinate ID is 5. So then even if you mess up, yeah, with something, yeah, yeah, it's crank. So Q. mm, So is it correct? Then the resolution of this plot. Yeah, it looks correct. Yeah, because it started at I think minus 30 degrees. Yeah, and then it should. Does it start at minus 30 degrees?
Yeah, minus 30 degrees. And then it decreases minus 1.2 billion per second.
Yeah. So at least visually it looks reasonable. Yeah. But so now it's a nicer question if the other bodies follows it as requested. It's a little challenging to check it. Of course, we could write here a function to visualize it. I think it's doable. It will take quite a while.
So look at the slide. Looking at the slide, like moves back and then moves forward again.
Yeah. We can use here slider and which coordinate? I think X. Yeah. So yeah, but exactly, it moves as described. Yeah, so it starts at some position. Yeah, that it's not maximum position. Yeah, because it was initially bended a little. So it retracts, gets to minus 300. Yeah, at the minimum position, and then gets back up to minus 700. Yeah. So at least this looks pretty intuitive because we also selected time step in the way that it should move, it should make at least around one full rotation. So it's quite clear that it behaves that way and that we don't have like very too many oscillations, yeah, because we use time step 5, so it should have 6 radians rotation, yeah, so it's not full circle, but even we can see that it's not full circle because it didn't get here, yeah. Also, those values, 700 for sure is correct one, yeah, because we can see that it's 300, 200, and 200, yeah. So when it's straight, it's 700, yeah. Is this value minus 300 correct based on this? Yeah. Yeah, exactly. Yeah. So at this point here, it's 200 minus 300 minus 500, so 300. Yeah. So okay, so everything looks good. So it's most likely our solution is correct. Yeah. Again, it would be great to be able to plot it here and see how it evolves in time. Yeah, it always helps, but it's a little involving. Maybe you can do this with ChatGPT quickly. Yeah. It should be able. Yeah. Yeah, because at least this part is a little tedious just to do. Yeah. Okay. Any questions? So should we try to do this kinematic analysis properly? I mean, calculate Jacobian of the constraints? So now we would like to calculate so we want to calculate CQ equal to constraints Jacobian of cis QT. Only cis Q. Yeah. Make sense? So this is our function. I have opened here constraints because it is kind of similar. Yeah. So C was the size of number of constraints 1. So what is the size of CQ? Remember? So CQ is the size of number of constraints, number of coordinates. Yeah. Because it's partial C, partial Q. Yeah. First is C. So the number of the columns is the same as in the C, but in the second direction if has coordinates. Yeah. And then also we can do the same trick with running index. Yeah. And then we will also have to loop through all the coordinates or all the constraints, yeah. But of course, all this part is incorrect. So let's leave it that way. We'll remove soon all not needed part. So what is Jacobian of our Revolut? I hope that I have it here somewhere. So we make position analysis and it's here. Ta-da. Yeah. So Jacobian for the Revolut joint is the most involving one out of the all the things that we have to calculate, yeah. And it's written here. Any questions to this? Or it's totally unclear what we have here? Okay, so firstly, this is equation for Revolut joint. Yeah. So we can see from this following that it depends on the coordinates only of two bodies, I and j. Yeah. So all the terms are zero except of terms related to c with respect to qi and c with respect to qj. Yeah, so only those parts can be non-zero. We can attack this problem on many ways. Yeah, one way is to just attack it directly. Another way is to use this description that is this then after getting time derivative of, for example, constraint. Yeah, we can find just what are the terms that are just next to velocities. But this is almost like definition of the partial derivatives. Yeah, because c dot is partial c partial q plus q dot plus partial c partial t. Yeah, standard way of calculating the full derivative. Partial c partial t is mostly zero, except of driving constraint, but it's not really relevant because we are interested more into this one. Yeah. So following the second approach, we can write the velocity equation for this vector. Yeah, in this form. This came from this term. Yeah, this term is constant. But okay, let's go through it. Yeah. So this is just position of the point. Yeah, and here is derivative of this point. So derivative of this point is r dot because it's coordinate clear plus a dot plus s. Yeah, because s is constant, local coordinate, so no derivative. Derivative is zero, so it's disappearing. And this derivative simply can be written as omega a and derivative of an angle. Can you recall it? Simply this works because a contains sines and cosines. Yeah, so cosine go into sine, sine into cosine, and with plus minus. Yeah, so it just transforms this matrix. Yeah, and this transformation is expressed as omega. And omega is very simple matrix that has, I think, -1 and 1. Yeah, so and this goes this results from the chain rule of differentiation that then when we differentiate sine, then we have cosine phi times phi dot. Yeah. So following this, we know that CQ simply has here identity matrix, yeah, because the transformation of this is identity matrix, if you put it here. And transformation related to the last third coordinate is this part, omega a s. No, it's not plus. Because it goes with respect to coordinates. Yeah. So it's not plus. So this is first two coordinates, xi, yi, and this is for the last coordinate phi I. Yeah. And here, of course, with respect to second body is the same, just with minus. And because here we have all those minuses. Make sense? Yeah. And to see what is omega, okay, it's written here, just not to forget it. So we can immediately write here a new function. Zero minus one, 1 is 0. Yeah, so this is already done. Okay, so we have to implement it. So we have to implement this. Yeah, and of course, if we would calculate directly partial C, partial Q, we will get exactly the same. Yeah, because here we have position, it gives identity matrix, and here this depends on the Q, and of course Q has to be transformed the same way. Derivative is derivative. Okay. So now how to put this into the code? So firstly we have dc dqi. Okay. So this is coordinates of those are constraints with respect to coordinates of the first body. Yeah. So what are the indices that we are using here? What are the value indices to put values into dc dqi? What the row indices stands for CQ matrix. It's written in line 5 of the code. Is it clear what I'm asking for? Okay, so we want to put this dc dqi into matrix. Yeah, and this is only a small part of this matrix. And it has this kind of expression. Yeah. So now the question is where to put it in this matrix. Yeah. So we have to index this matrix. Any idea how to index it? Yeah. Yeah, exactly. The first one is the row because it refers to the constraints as written here. So it must be the same like here. It's just the constraint equation of the body. And what is the second index? Yeah, of body I. Exactly. So our coordinates of body I. So it's body I index. Yeah. So exactly as it's here, it's body I index. Make sense? Yeah. And then we have to just write this equation here. Yeah. So it's I of 2. This is that one. Yeah. And the second one is just this omega. So omega, we define it area times AI. We have calculated AI also already. And times local vector at body I. So times local UI. What do we need? new function? Or brackets? Yeah. No, we don't have to. Okay, we discussed this, but it's not so important. It's implementation detail, but we don't have to. And you can check it here, that it will work. Okay, it doesn't work because we hide it. So now it will work. So I think that we have to change it here because it will, yeah, so this is one of those chibats and small implementation annoyingness, yeah. Yeah, now it will work. So why does it work? It works because of the MATLAB. Yeah. So in MATLAB, we briefly talk about this. Yeah. But in MATLAB, it works that way that you have function that takes no arguments. You don't have to provide parentheses. Yeah. So I think that the same pi is most likely function. Yeah, and when you call this function, it gets you the value of the pi. So okay. So it should work. Make sense? Why this is that way? Yeah. And of course, then we have to do the same for this part with respect to qj. Yeah. So the difference will be, so the first index is the same because we are working with the same set of coordinates, constraints. Yeah. But here we just put it at index of body j index. First difference is that here is minus. Yeah. And then we have aj and local uj. And I think that we don't need this anymore. So this is dc dqi. So that part is dc dqj. Any questions? No questions. And so, but again, any questions or is it clear? When I show it, is it clear? Yeah. So when you will try to do this by yourself, maybe it will be not clear, but then, we can discuss about this. Yeah. And now let's clean a code a little. So it complains that those values are unused because they aren't. So let's get rid of them. And now it's fine. Yeah. So for simple constraints, Jacobet is even simpler. Yeah. So for the simple constraint, we can just write CQ of current index plus 1 and coordinate index is equal to 1. Make sense? Because we are just writing that Q of coordinate index minus something. Yeah, this is constraint. So if we calculate dc dq, yeah, we are just exchanging this into 1. Yeah, and the position of this 1 is of course coordinate index. Yeah, so that's why CQ at current index of the constraint and coordinate index is simply equal to 1. So we don't even need this value. And same goes here for driving constraints. Yeah, for driving constraint, it's exactly the same story. This doesn't depend on the coordinates, it depends only on time, so it disappears. And here we have just a reference to single coordinate as linear function, and partial derivative of this coordinate with respect to itself is 1. So we have 1, and this is the place to put it. And we have Jacobian. Yeah. We have Jacobian. So firstly, so we can use it. Yeah. So firstly, we can simply check if it works. I have something so it doesn't sound good. Yeah. So okay, because I clear the stuff of conflicting definitions of the omegas. Yeah. So let's run all the code. Yeah. So it solves. It shows this again, but and we have no errors here. So it means that CQ at least was calculated reasonably. So we can take a look at CQ. Yeah. And it is filled in with some values. Yeah. And now we can roughly check if it's correct or not. Yeah. Does it look correct? Hard to tell. Yeah. But if we would, so first 6 equations were equations for revolute joints. Yeah. And first revolute joint was between the ground and between crank. Yeah. We can check it into the code. Yeah. That it was between the ground and the crank. So at least it looks reasonable, yeah, that it belongs to the correct coordinate set, because here we have equations, constraint equations, and here we have coordinates, as we described. Here we are expecting to have identity matrix, it's there. Then all the transformations from the ground are 0 because okay, where we have here we have this equation, yeah, because this is identity matrix, but this vector is 0, yeah, for the ground. So it's 0. Here is -1, and then there is some just some vector. Yeah, makes. We can check it or not. Yeah, but it looks. I think it looks pretty reasonable. Here is similar story. So the second revolute joint is between our crank. Is between crank and shaft. Yeah, crank and shaft. So two next bodies. Identity minus identity, some values. And the third revolute is between the shaft and slider. Yeah, again, identity minus identity. Here are zeros because slider. We attach it to the center of the slider. Looks reasonable, yeah. Then the next 5 constraints are simple constraints. Yeah. The first one, we're constraining ground to 0. Yeah. So we can see this one's here. And the last 2 simple constraints were constraining 2 last coordinates of our slider. And it's clearly visible here. Looks fine. And the last one is here. This is driving constraint. And driving constraint was imposed on our crank, rotation of the crank. We already learned that this is ID number 6, and it's here. Any questions? At least it's consistent with our implementation is consistent with our knowledge about the analysis of this kind of the system. So this looks promising. Okay, you can check it manually if you want, of course. Yeah. Okay. So what is the next step? Why we have a Jacobian? Yeah, interrupts. So we don't have Newton-Raphson here, and we don't want to write it, but I think that it should be here. Newton-Raphson method, yeah, it's here. So let's copy, get back here, planar multibody. Let's paste it. Okay, so we have already Newton-Raphson method. Yeah, that's good. We just used exactly the same that we have seen previously. And the aim is to okay. So now we would like to have a function called solve kinematics that will use Newton-Raphson method to solve for position. Yeah. So yeah, let's create this function. Hmm. Okay. Okay. It was some error, but now it works. Okay, I will copy paste this solution. Yeah, because all the other parts are the same, because all the preparations parts are the same, and we just have to replace somehow those two lines. Yeah. So because we need initial position, yeah, we need to define T, we need to make place for Q for our solution, yeah, and yeah, the looping will be very similar. So most likely function is even the same. So, but instead here, we don't want to use fsolve, yeah, we want to use our Newton-Raphson. So take a look on the Newton-Raphson. Let's get it. Yeah. So Q is Q current. Do we want to also return iteration counter? What should we do with iteration counter? Should we store it somehow? Yeah, I don't need it, but it's also good for checking how our solution is progressing, because it should be pretty uniform, and this value should be small. Yeah. So we can consider storing it, yeah. So we can store it, and it should has size of NT. Yeah. Yeah. So now we have to provide to Newton-Raphson f, which is our function, yeah. And our function is, of course, constraints, yeah. So then we have to provide Jacobian, yeah. And it will be similar case, yeah, that we'll have to wrap up our constraint Jacobian function, yeah. So it's constraint Jacobian, and constraint Jacobian gets cis and q, yeah. So J is wrap up, Q, X, I mean, is initial guess for Newton-Raphson, so it's just Q last. Make too many clicks and somehow open that dictionary. Okay, and tolerance. And tolerance, of course, we have to specify. Yeah. So we should specify some tolerance. What is good value for tolerance? Okay, so it sounds reasonable. Yeah. And if we are calculating it, let's return it. Okay. So it should work, I believe. Yeah. Yeah. Let's add it here because we make this modification and just let's test it. Okay, well, good thing is that we didn't get an error. Yeah. I will create new variables to avoid confusion with the previous solution. Yeah. Again, no issues. Yeah. So now getting norm of the constraints is even more critical because for the f-solve, we can assume that it works. Still, maybe it's sometimes better to check, and can be many reasons for it not to solve. Yeah, but norm of C using Newton-Raphson. Yeah, let's put it here and here and here. Unfortunately, yeah, this is the issue when you use variable in many places and haven't right function for it. But I hope that now it's fine. An error, an error, an error, an error, an error. Norm of C. C is just here. Yeah, so this should be fine. Okay, it shows some fluctuations. Yeah, but nevertheless, here the constraints are met up to the precision of 10 to the minus 10. Yeah. So I think it shows even better precision that for f-solve, because I think it was 10 to the minus 8. Yeah. We can also check how many iterations were taken. Oh no. Yeah. So yeah, I forgot to put. So zeros of NT, for example, 1. Yeah. Now it will be better. Again, yeah, this works fine. And now an error can be read normally. And as we can see, for our test, we have consistently always 3 Newton-Raphson iterations, yeah, which is adequate, yeah. And I think that here we could clearly see what would happen if you use Q0, for example, yeah, all the time, that then number of Newton-Raphson iterations would increase. Yeah, do you want to check it? Yeah, because then it would mean that we have always this Q last equal to Q0. Okay, it's solved. System is pretty simple. So firstly, the constraints are met with poorer tolerance because it's 10 to the minus 8. It's still okay. It's within the tolerance. We set tolerance to 10 to the minus 8, yeah. So it's reasonable. But if you take a look on the number of iterations, we can see that, this number is increasing. Yeah. So we get even up to 11, yeah. So, and of course, this is the most costly part. Yes, we have to calculate the Jacobian matrix, then solve the equations of motion, not equations of motion, but those nonlinear equations. And as you can see here, we need far, far more of those, calculations, just by this very simple change. So let's revert back to the correct one. Yeah. And now, yeah, we have those expected 3. So it makes quite a big impact. Yeah. And then we can do the same. Yeah, and just check if our, for example, slider is moving as expected. So T and R, Q and R, and R. Yeah, and the motion is as expected. Yeah, so we get exactly the same plot. Around 300 here, minus 300, minus 700. Yeah, so even the scale is the same. The plot is exactly the same. Yeah. So, of course, those two solutions works the same. Questions? Perfect. Okay. So what could be the next step? The next step is velocity analysis. And because it's it's very simple, so we can do this because we still have like 10 minutes, let's say, yeah. So, and we can still do this. Okay. So velocity analysis. So to add velocity analysis, we need CT. Yeah. CT is partial C, partial C, partial C, partial T. Yeah. And as it's written here, yeah, it's 0 for all our coordinates constraints except of driving constraints. Yeah, for driving constraints, it's non-zero. Yeah, just like that. So we need a function that calculates our CT. Yeah, it's constraints dt. Yeah, and it takes system Q possibly and P. Yeah. So we need this kind of function. Of course, it's also based a little on our constraints. Save it. It's based on our constraints. The difference is that firstly it's CT, yeah, and secondly CT for revolve joints is 0, yeah. So we can set current index based on this practice to this expression. Yeah. So because this means that we can skip all revolve joints. Yeah. And this means that we can just skip all the simple constraints. Yeah. Okay. So now it is just about our driving constraints, and we need for it, for CT, we don't need coordinate. We just need minus And we need derivative of our coordinate function. How to get the derivative of our coordinate function? What? Yeah, we could. Or we can just use hand differentiation. Yeah. In either case, whatever we decide to choose, yeah, you can equip it with symbolic differentiation, of course, yeah. We just need to add it here. So I just open this R to drive a constraint, yeah. So then we'll just add coordinate function dt, okay? So we'll just add it here because we need it for analysis. So we need it here, yeah. And this equation is so simple that I will just calculate this derivative by hand, yeah. So this is constant term is missing, and this is t, and of course, coordinate with respect to t will be just this constant value omega cis, yeah. And this solve this task, yeah. So now we can get dt, yeah. Now it should work. Of course, when we run it, it doesn't work because we have to refresh the whole file because it's not in the memory. But when I just calculate everything again, it shows us the last result, but CT is calculated and it has value all the zeros and 1.2 as expected. Also, we have minus. And now what we can do with this CT? We use it for kinematic analysis. Yeah. So we get back to solve kinematics. Yeah. We declare that we will return not only Q, but also we will return DQ or Q dot, maybe Q dot. Yeah. Yeah. Q dot will have, of course, the same size as Q. Yeah. And here we have Q current, and we have to calculate Q dot. Yeah. So to calculate Q dot, we simply have to solve this equation. Yeah. So left-hand side is Jacobian. So it's just J of Q current. And the right-hand side is minus CT. Yeah. So it minus constraint dt. And constraint dt takes Q cis, Q current, and T. And it should work. So this is not nice because now we will have so I will cut it here. And now we can repeat this analysis, having QR and Q dot and R. Yeah. It seems that it works. Yeah. It provides some values. And we can make some plotting. For the velocity of our slider. Yeah, it's a little hard to tell if it's correct. Yeah, but we can then we can approximate we can approximate the velocity using position. Yeah, using position. It will be a little crude maybe, but we can at least try to do this. And -1. So then we will have to approximate it using finite differences. We will have Q index of 1, 2 to end, minus Q and R of 1 to end -1, and then divided by time step. Maybe it's not perfect. If we improve the time step, it would look much better. Yeah, but we can see that it follows the correct trend. Yeah. So even this cruel approximation using these finite differences provide us, shows us that the solution looks reasonable. Yeah. So that's good because it's also very easy to make some kind of stupid mistake, like put minus somewhere. Yeah, like forget all those minuses. Yeah, like here. So I think that it's correct. Okay, and it closes our session for today about programming. Any questions? Everything is clear? Okay, good, good. There are some smilings. Nice. Next step is acceleration analysis. Yeah, and here it's written how to do this. So for acceleration analysis, you have to calculate G, because this side is already the same. Yeah, so this is Jacobian. This is Q double dot. Yeah. So to make position velocity to make acceleration analysis, then it means that you need here new Q dot dot. Yeah, and simply solve J, and here have this G vector. It's called gamma G, whatever. Yeah. But you have to calculate those G's. Yeah. And here it's written how to, okay, so you can either use this expression. This is one way. Yeah. Another way is to use this expression. Yeah. So we can compute C double dot. Okay. Like time derivative. Neglect acceleration terms. Okay. Because acceleration terms are here. So you're removing them because they are on other side, and then negate because it's on the other side of equation. Because C double dot is equal to CQ Q double dot plus G minus G. Okay, so this is the reason why this works to calculate G. Okay, and I think that it's this way it's much simpler than going through those partial derivatives. You can use those partial derivatives, all those for checking. Okay. So here's example of how to calculate it for revolute joint. Yeah. So here is equation for revolute joint. Yeah. Here is, we already calculated what is the expression for R double dot. So position vector of double dot, it's like that one. Yeah. So then second derivative of revolute joint is like that one. Okay. Simply followed from this one. So it has acceleration terms here and here and here and here. Yeah. So we can simply neglect those acceleration terms. You already can see that those are really the terms that appears next to Jacobian identity matrix A omega AS minus identity matrix minus omega AS. So it's clearly already there. Yeah. So we are left with those two quadratic velocity terms. And those are always quadratic velocity terms, oh, except when it's t. Yeah. So sometimes it's different. But here we have those simply those quadratic velocity terms. Yeah. And when we negate it, we get G for revolute joint. So here we have already ready-made expression for G for revolute joint. Make sense? For simple constraints, it's even simpler because for simple constraints, G is equal to 0. And for simple deriving constraints, is simply equal to negative CTT. Yeah, so second derivative of your function. You can check it very easily. And here's your task. Implement missing features. So support for translational joints. Okay, this is the most challenging, I believe. Kinematic analysis on acceleration level. We already discussed how to do this. Yeah, so we have to calculate this G matrix. Yeah, and the most challenging, of course, is to calculate this G matrix for translational joint and analyze some mechanism that was not analyzed. And please do not analyze pendulum. It's far too trivial. And to analyze pendulum, it takes like 10 seconds because you just take this file, remove this stuff, then remove all related stuff, yeah, and it's done. Yeah. So, like 5-second work, it doesn't sound, like a thing, yeah. So find some nice mechanism, yeah, to analyze and analyze it. Yeah. I don't know what you can have in mind that it's not realistic, but yeah. Because then I think that all the mechanism or most of the mechanisms that has just several parts were already invented and used in one way or another, yeah. So yeah, so you can do whatever, yeah, but yeah. But it has to fit into our here task. I think that even here on those slides, there was one mechanism. Not here. Here is for quick return mechanism that it's one, just doable option. Yeah. It's really nice because here it has translational joint, revolute joints, revolute others. Here we can use simple constraints or translational joints. Yeah. But yeah, you are free to choose whatever. Just make it more than one body. So like three, preferably. Yeah, 3, 4. Yeah, it doesn't really matter because then adding those is very similar. And here I put 2 weeks. Yeah, if there will be some issues, maybe we'll extend it to 3 weeks. Yeah,
So it's now the exercise of
I think you can treat it as a project. The rules are practically the same. Yeah, maybe you can write this report a little longer because it will have a lot of figures, but still 2 pages of text should be more than enough. Okay, so we are just right on time. Are there any questions?
what thing, or can I use one? I abbreviated some of the stuff here. Can I also use this? So it functions the same as your code, but
Yeah, you can.
Also analyze this, but it's better with time But we are supposed to conclude that the simulation works as expected. Just this.
What?
When in the report, we need to define a system and analyze
Yeah.
it. And
And then conclude that it looks, yeah.
process.
Yeah. So yeah, well, you have three parts here. Yeah, support for transactional joints. Yeah, to show that it works, you can test that with your transactional joint. Yeah, this system works. Yeah, and then so it's good to provide equation that you use in the report. That it's obvious that you don't use the same file but change its name. Yeah, because I have seen this kind of the solutions. Yeah, it's it's not optimal one. Yeah. Kinematic analysis on acceleration level, yeah. So you show solution on the acceleration, and for example, maybe you can use some kind of again this approximation of based on velocities to show that acceleration are reasonable. And the third part is somehow to show the mechanism and describe, it contains 5 bodies, yeah, or whatever, yeah, it has this kind of the joints, yeah, here is the driver, and it gives this solution, and this plot indicates that it behaves as it should. Stuff like that. Any questions from the audience side? No? Yes, we're ready to go for our other tasks. Okay, so thank you. And yeah, and that's all for today.
Thank you.
Thank you. So I will stop recording and yeah. Bye-bye.
Thanks.